Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so happy Ganesh Chaturthi. It is Ganesh Chaturthi here in the United States as it is across India, and I want to wish all of you a wonderful Ganesh Chaturthi, and I also want to wish all our NEET students who will be heading to the exam hall just now. I want to wish them all a very successful NEET exam. All my best wishes, best of luck. Please manage your time well. Please read your questions carefully, as we always remind you. So please continue to study. Those of you who are, now entering class 12, please continue to study. It will be your turn before you know it. So with that, this is for the NEET students. JEE students, I know many of you took the exam last week, and some of you may be planning to take it again in January. You're, I think, allowed 4 attempts. So please continue to study. Please stay focused. What has passed has passed. If you did well, then think about how you want to deal with the next part of the equation, which is the advanced exam, and get yourself fully ready and continue to exercise. Take all the other exams. There is BITSAT where there is VTI, VIT exam. There are many other exams. Amrita has an exam. We have a special relationship with Amrita. So be well engaged with all the programs. Whether you are a JEE student or a NEET student, engage well with all the programs. Take, put your education first. Do not get too caught up in success and failure. They are part of the same fabric of life. And remember that is a very important lesson. You try hard, you strive hard, then you leave it to Lord. Okay, and always pay careful attention to the questions. Read them well, manage your time, and that is why we now have a mock test as well, application as well. So with that, let me get started for today. I always start with our today we are going to continue with waves, but before that, let me complete the work that we do advertising our program. So for students who are getting ready for NEET 2022, download the app. There is no better time. It is now available in the period for the promo period has expired. Now we are in mid-September, so it is now available for students. You can go to com.jnanamarga.sushruta and let us know if you need any help with downloading it, registering, etc. And also if you need any financial help, But we are back to the normal pricing with the app. The second app is Ramanujan for JEE, our trademarked app for JEE students, now available. You can try both apps. This app is also, you can try it free. You download free, you spend a couple of weeks, and then you have to make a purchase. So now today we are going to continue with the discussion, but I'm not going to start with too much of what happened last week. I am going to start out with this equation. I'm just going to go over the details of it. The general one-dimensional differential wave equation, dou square f by dou x square equals 1 by v square dou square f by dou t square, where v is the velocity, and x is the direction in which you are moving, and we already discussed some of the details. The wave goes through a maxima and a minima, and the most important ideas: the period of the wave is 1 by the frequency. The wavelength is related to the velocity. The velocity divided by the frequency is the wavelength. The frequency times the wavelength gives you the velocity. F lambda equals v. V is the velocity of the wave, right? And we already discussed also the second form of this equation, where we rewrite the equation in the form a sine kx plus or minus omega t. Omega equals 2 pi by t. K is equal to 2 pi by lambda, and therefore uh, omega by k is equal to v, right? V is equal to f lambda, right? Omega equals 2 pi f, right? And k is equal to 2 pi by lambda. The 2 pi's will cancel and you will end up with f lambda when you divide omega by k. Okay, so omega by k equals v, and v is equal to f lambda. All right, so remember all these relations. Let's take a look at one problem. Displacement y of a wave traveling in the x direction is given by 10 to the power of minus 4 sine of omega t minus kx, right? So now what is k, right? What is omega, right? Omega is the coefficient of t, or t, whatever sits next to t is omega. 600 is omega, right? What is k? K is 2 or minus 2, right? So omega by k will give you the speed, right? Omega is 600, k is 2, so 600 by 2. The velocity speed of the wave is 600 divided by 2, and the amplitude is 10 to the power of minus 4, right? So we already discussed transverse and longitudinal waves, and the speed of sound is given by the square root of t over mu, where t is the tension, constant uniform tension. T gives you the tension of the string, guitar string, veena, sitar. T is the tension of the string, and mu is the mass per unit length. So remember that, and so based on that, the corresponding v, the speed of the wave on the string, is given by the square root of t over mu. Okay, speed of sound in a medium also follows a square root of the bulk modulus divided by density. Okay, so these are two sides of the same coin in some ways. Bulk modulus is similar to tension, and rho is the density of the medium, and the other case mu is the density of the mass per unit length of the stretch string. All right, so now let's take a look at this one. Uniform string of length 20 is suspended from a rigid support. A short vapor is introduced at one end. It starts moving. The time taken to reach the support is, so how long does it take to reach 20 meters, right? Yeah, so now for this one, you know that the velocity is square root of t by mu, and t is proportional to, is changing. It is proportional at each point to the mass below it, and the mass. So if you are x above from the bottom, it is mg times x by l, right? So that is the tension at each point, right? So now velocity dx by dt is mgx by l, right? And mu is mass m by l, right? So the m and l cancel, and therefore you just have root of gx. Now you do integrate both sides, you end up with t is equal to 2 times root of l by g, and g is 10, l is 20, 20 by 10 is 2 root 2, right? So you have to do this particular integration, right? So beautiful question, and you should understand how to manipulate these ideas. Then we discussed various ideas in terms of the relationship between motion and simple harmonic motion, uniform circular motion. Wave motion is related to uniform circular motion in many ways, and also simple harmonic motion. We already explained in the last class. If there are two or more coplanar waves arriving at a point in space at the same time, then the net displacement is given by the sum of all the individual displacement of the wave. So this is a very tricky idea. So in the sense, the nuance is not that tricky, And this is called the law of superposition. Okay, law of superposition comes in many places in physics. The most common law of superposition is when multiple forces act on a body. Just take the vector sum, right? Then it happens in, we have multiple voltages, right, in a circuit. When you have multiple, like that here, then there are multiple waves that happen at the same time, right? You will always have multiple things happening at once. So now, in the case of there is a linear addition, and of all the waves. So the F1 plus F2 plus F3 will sigma Fi will give you F net. That's what the law of superposition of wave states. And because it's a linear addition, right? We still satisfy the linear differential between dou square f by dou x square equals 1 by v square dou square f by dou t square. Notice kx, right? If you differentiate twice, you do end up with, remember, v is equal to omega by k, right? V is equal to omega by k. We went over that, right? V is equal to omega by k, right? So when you differentiate twice, on one side you will end up with omega, and on the other, or omega square, on the other side you end up with k square, right? And therefore, the k over omega square comes from the two differentiations that you do. Okay, so one dou square f by dou x square. Remember, it's a partial differential. So if it is a sine wave, you will come back to sine, and then if the other is also because sine kx minus omega t, the other is also a sine wave. Because of that, you will end up with omega square over k square. Okay, so and that will then lead to your 1 by v square, right? So so keep that in mind. So let us take this look. Let us take a look at this one. Notice that where the v comes, right? Omega over k, right? So the omega will come on this side, and therefore you have the corresponding equation, right? So now, if you had the sine wave, right? A1 sine k1x minus omega 1t plus A2 sine k2x minus omega 2t, etc., etc., right? So what is important is that these waves, they don't share a frequency. Okay, they don't share an omega, and therefore the reflection of waves on a string tied to a support, right? So this is the simple case, right, where you do that. One end is tied, the other end is free to move. So you do a push, and then the wave trickles down at a particular speed, right? Now, when you have a reflected wave as well, right, then there is a superposition of these two waves. Okay, now the incoming wave is a sine omega t minus kx. The reflected wave is b sine omega kx plus omega t. Okay, so the reflected wave and the incoming wave are different in the coefficient. One is a minus and the other is a plus for omega t. Okay, and therefore, what happens is, when you add the two, right? If there is, if they are in lockstep, you will then have, a sine omega t plus b sine omega t. If a equals b, then you will have no wave, right? But then if there is a phase displacement, then you will have a different kind of wave. Okay. Now, the phase displacement, right, is what happens, with respect to the standing wave. So if you had a standing wave at a fixed point in time, a sine omega t. The other one will be a sine minus omega t plus pi. Okay, therefore you end up with two waves. Okay, get this wave, we add a phase of pi to the phase of the incoming wave. This is due to the fact that the argument of the incident wave is minus omega t while that is the plus. So now when we add these two waves, a sine kx minus omega t plus a sine kx plus omega t, you can then expand the two forms, right? You become a sine kx cos omega t, sine a cos b minus cos a sine b, right? And therefore, two terms will cancel. Which are the two terms that cancel? The cos terms cancel, right? The sine terms remain. Therefore, you have 2a sine kx cos omega t. So that is the equation of a standing wave. Now, standing wave is superposed when there is one sine wave this way, other sine wave this way, and they both are in the same phase. Now, so now notice that even though a wave equation is not of the form, this is the fact that it is not a traveling wave. Okay, so there is no kx here. So because of that, there is no velocity, right? Velocity is omega by k, right? And in that sine kx minus omega t, but actually this doesn't have that kind of a form, because the sine term is outside, the cos term is outside. You have a standing wave. Therefore, the velocity of that wave is zero. Therefore, it can be visualized as saying that every point in that string is at any time you have a sine wave, right? And at every point, if you see over a period of time, you will have a sine wave like that, So it is what is called the ensemble. They have this term called ensemble. It is a term from music. Okay, so it means that an ensemble is when there are many players who are playing parallelly. Okay, and therefore the ensemble. So at any given time, there is a sine wave. Now in an ensemble, typically everybody is expected to be playing at the same frequency at the same time, not out of phase. You have to get the timing right and you have to get the frequency right. Otherwise, you will just hear a cacophony of sounds, and the conductor will be glaring at all the people who are missing the note. Okay, so that is the important thing. We used to have one T.R. Papa, very famous man in Chennai. Anyway, so various forms of standing wave equations: a sine kx cos omega t, b sine kx cos omega t, etc. And the choice depends on the form of the initial wave and the reflected wave. So now, if there is a, if you have, so standing waves are of two forms. Okay, you can have a standing wave when the string is fixed at both ends, right? So now, then you will have a standing wave, standing wave, standing wave, standing wave, right? And the other case is when the string is fixed at one end and then you shake it and then you keep shaking it, then you will have a lot of signs, it will keep move the sine wave, right? So now in those circumstances, you have a standing wave. Now, when the string is fixed at both ends, you have a sine kl cos omega t, right? So under those circumstances, where kl, L is the length of the string, KL, sine KL is equal to 0, right? So K is what? Wave number 2 pi by lambda. So 2 pi by lambda, right? So KL should equal n pi, and K you already know is 2 pi by lambda, right? So what is lambda? Lambda is V is equal to F lambda, right? So it is V over S. Okay, so K will equal 2 pi F by lambda. Okay, so 2 pi F is what? Omega. Omega by K equals V, right? So 2 pi V over 2 pi mu over v. In this case, the bottom is the velocity and the numerator is the frequency. Right? So then the frequency has to follow, so you plug that in, right? You plug that KL equals n lambda and K equals 2 pi mu by 2 pi mu divided by V. Okay, so the pi will cancel, there will be a 2, right? And therefore the V, right? The V is then related to V, this is the frequency. The frequency at which will produce the standing waves, right? So when do you end up with a standing wave, right? The displacement must be 0 at both x equals 0 and at x equals L, right? So that is when you end up with a standing wave. Now, the standing wave, in this case, the frequency of the wave will be n times v by 2L. And v, as you know, is square root of t by mu, right? So from earlier, we looked at the velocity equations, where t is the tension, mu is the mass per unit length, right? So n by 2L. Now, if you had a string tied at both ends, Vn will equal n by 2L times square root of t by mu. Okay, so that is when you have nodes, and the high and low point nodes are where you have the amplitude is 0, and the high point is where where it oscillates the most. These are called antinodes. Okay, you get the maximum amplitude at the antinodes. N by 2L times t square root of t over mu. Now, if the string is fixed at one end, right, then you end up with something of the form a sine kl cos omega t, and you set the sine kl equals 1 because it's free at the other end, right? So it's free at the other end, so the other end can be 1. The previous case, both ends have to be 0. Now, the one end is 0, the other end is 1. Therefore, sine kl will equal 1. So when does sine kl equal 1? Sine kl equals 1 when n plus half pi. 0 plus half pi, right? When sine pi by 2 is 1, right? So sine pi is 0. So plus a pi by 2. You just keep adding a pi by 2, right? So so sine n pi by 2 has to be 1. So you will end up with cases when you have 2n plus 1 by 4l. The previous case we had n by 2l. Now we have 2n plus 1 by 4l, and the will be the frequency. Okay. So these and correspondingly, right? If you have a frequency like that, the wavelength will be 4l. So how do you get the wavelength, right? The wavelength is v is equal to f lambda. So this is v, right? So square root of t by mu is v, right? So v divided by mu will give you lambda. Okay, so 4l by 2n plus 1 will be your lambda. The previous case also we had a lambda, right? Previous case there was also a lambda, right? So distance between nodes is equal to lambda by 2, right? In this case also there is a lambda. Lambda is v over mu, right? So 2l by n will give you lambda. Lambda is the wavelength, right? So in this case, 4l by 2n plus 1, that case it is 2l by n. 2l by n will give you lambda. Okay. So now a standing wave is formed by superposition of two waves traveling in opposite directions. The transverse displacement is given by this. Calculate what is the speed of the wave? Speed of the wave is k, and omega, right? Omega over k, right? It has to be of this form. solution has to be of this form, right? So it is already of this form. They've already written it down in this form. So you just have to look at the omega, pull out the omega and pull out the k. Omega is 200 pi. K is 5 pi by 4. Divide the 2. Now we are going to discuss the next set of ideas relating to standing waves. Now you have two kinds of pipes. You have pipes where there is one end which is closed, and then you have pipes where like that, right? Both ends are open, right? We already looked at stringed instrument, both ends are tight, right? Now the pipe is a little bit different. There are two types of pipe. One pipe where one end is both ends are open, and the other pipe where one end is closed. Okay, sure, you've seen the flute and the trumpet, right? Now if you are open at both ends, you need a wave like that. It has to be a and therefore you have to have open end implies the pressure difference between the ends and the atmosphere is 0. So pipe open at both ends is analogous to a string tied at both ends. Okay, so string tied at both ends, we already looked at that, right? If you remember, string tied at both ends, n by 2l times square root of t by mu. We already told you that t by mu is the same as b by rho. T by mu is same as b by rho, right? And therefore, you kind of look at the same story, but with a slight difference. Okay, the standing wave in a pipe is of this form: 2 pi by lambda equals k, and k will equal n pi by L. Okay, and therefore your lambda equals 2L over n, just like the previous case. 2L over n in this case was also lambda, right? So here also 2L over n. Okay, and n, what is this n? N is the number of waves. Okay, so now if you had one wave, two waves, three waves, right? So you need at least one wave. Okay, and so that is the and each additional wave where is called a harmonic. Okay, so or you need at least half a wave. That's why you have the two. So you already know the velocity is b by rho, square root of b by rho. So you plug that in. In this case, you have velocity square root of t by mu, right? And therefore, the v mu n, which is the frequency, which is the nth harmonic. The first harmonic is where n equals 1 is v by 2l. Frequency is v by 2l. L is the length of the instrument or the pipe. Okay, so v by 2l will give you the first harmonic, and then you will have the second harmonic, which is 2 times v by 2l, 3 times v by 2l, 4 times v by 2l, which will give you each of the higher frequencies. Okay. So now string example. Why do we do these examples in the second class? It is so that you pay careful attention and solve some actual problems. You download our app, go and do more problems yourself. Listen to the lectures that are also available inside the app. IIT lectures, excellent. Our lecture is only one part of of your learning. Look at the same slides are available there also. Look at the slides, look at the and also look at the IIT lectures, and then do problems. Now we have added assessment essentially for all of you to be able to take advantage of it. Anyway, let's look at this problem. A string is stretched between fixed points separated by 75 centimeters. Okay, is observed to have resonant frequency 420 hertz and 315 hertz. Okay, there are no resonant frequencies between these two. Okay, so NV over 2L is 315. The next one, n plus 1 v over 2l is 420. Okay, was a fixed string, right? So n v over 2l, 315, n plus 1 v over 2l is 420. So now, how do you get n out of the equation, right? You just subtract the two. V over 2l is 105, right? So when you just subtract the two, you end up with V over 2l. Then the lowest resonance frequency is 1 V over 2l, right? So the lowest resonance frequency is 1 V over 2l. That is the lowest resonance frequency. That is 105 hertz. Okay, so very simple question if you understand the material. Okay, now if you have a closed pipe or a string which is free to vibrate, which is free at one end, right? In the previous case, the veena, both ends are tight, right? They will push it till it becomes tight, right? Then you will have a standing wave with both ends tight, right? Now you have one end which is loose, okay? And when you have one end which is loose, you have, or a pipe with one end closed, then you have a different kind of harmonic, different set of harmonics. So here your lambda equals, so in the previous case we had nv by 2l. Now we have 2n plus 1 v by 2l by 4l, right? 2n plus 1 v by 4l is the harmonic, right? 2n plus 1 v by 4l will give you the harmonic, right? So the nth harmonic 2n plus 1 v by 4l, right? And so vn will 2n plus 1 v by 4l, right? So now that will be each of the frequencies, right? So so this is in the case of so look at the lowest harmonic is just a quarter wave, right? Like that, right? And the second one is the 1.5 wave, right? And therefore you end up with this equation 2n plus 1 v by 4l. So at n equals 0, you have the half wave, or just this, right? So and then correspondingly you have the now there is this other thing called N correction. Node at the open end occurs at a distance slightly outside the open at approximately 0.6 r units from it, where r is the radius of the pipe. Okay, so that is a end correction. End correction case, it happens little bit outside the pipe. Okay, so because of that, if you have a closed pipe, you have 0.6 r added to the length, and you have 1.2 r added to the where r is the radius of the pipe. So you have 1.2 r added to the for an open-ended pipe. Okay, for a closed pipe, you have 0.6 r. Open-ended pipe, there is 0.6 r this side, 0.6 r that side, right? The closed pipe, you have 0.6 r only on one side. Okay, so now, so that is what N correction. Okay, so now the other idea we have to discuss is this idea of beats. Okay, what is a beat, right? I'm sure you have heard this term beat, right? Beat is when the standing wave is made by two different waves with a slightly different frequency. Okay, now when the two waves of the standing wave have slightly different frequency, then you will get a variance of the, then you'll have a what is called a envelope, which reflects also a second wave, which is a very slow wave, and which reflects the which is of the frequency, which is the difference of the two slightly varying waves. So when you superpose the two waves, you will have a net wave which is not exactly the each of one wave or the other, but it is the arithmetic mean of the two waves, right? And there will be a second beat which is omega 1 minus omega 2 by 2. Okay, And so this one is related to the beat. This one is the effective uh, uh, frequency of the wave. Okay, so when you plot it, you have an omega plus, omega minus, the and the envelope is given by the slower wave. Okay, the envelope, right, reflects the heat. Okay, therefore you have the red line which represents the envelope curve, and the blue line which represents the rapidly varying wave. All right, therefore you have 2a sine omega plus t and cos omega minus t. Okay, so from these two, you have a beat frequency omega 1 minus omega 2, right? And when omega 1 is equal to omega 2, you have beat frequency of 0. Then you just have a common omega, right? Otherwise, you have an omega plus and omega minus. Beat frequency is omega f1 minus f2. Rhythmic rise and fall in the amplitude of the resultant wave is the beat. Okay, so that is when like that you will get a second wave. Okay, now therefore we get superposition of two waves, both showing beat phenomena. So the final resultant wave also shows beat. So when this happens also when you have two waves of different amplitudes, right? So when you have two waves of different amplitudes also, you end up with one wave, right, which then ties to the resultant beat. Okay, so now I'm going to deal with the last idea that we are going to discuss, and maybe we will do a couple of problems next class as well relating to this. This one is this idea called Doppler effect. Okay, now when does Doppler effect occur? Okay, when there are two sources, right, with one of them which is moving, or both of them are moving. So there is a relative movement of the two sources. One is hearing, and the other is the source of the sound or whatever. Okay, or source of the wave. The other is hearing it. Okay, now. Doppler effect is used in so many places. Okay? It is used in radar. It is used in sound detection. Okay? Sonar. It is used in so many other places. Doppler effect starts to matter. Okay? But it is essentially this. If there is one, the source or the listener or the destination of the sound, one of them is moving, there is a relative change in the frequency that is heard. So now when one of the sources, instead of just moving at a given velocity, is accelerating, then you will have a continuous change in the associated frequency. Moving at a constant velocity will have a particular frequency, and if it is changing velocity will have a changing frequency. Okay. Now first, let's take the case when the relative velocities are given. Okay. So now the source is moving. Let's take when it is moving towards the observer. Okay. There is a train coming towards the station, and there is a whistle. Okay, and you are standing at the station. Okay, so now the train is moving towards you. What is the mu is the frequency of the whistle, right? This is the frequency or eta. I don't know, mu. I think mu is the frequency of the whistle, right? And what is the frequency that you hear? Now that frequency is changed by the v, which is here v is the velocity of the wave. Okay, velocity of sound you all know, right? V is the velocity, the speed of the wave, right? the speed of the wave is speed of sound, 330 meters per second, right? Now the train is, let's say, is moving at 6 meters or 10 meters per second, right? So now what will be the and it the view emitted will change correspondingly. Okay, if the speed of the wave is heavily is very close to the speed of sound, right? Then this value will start to grow. Okay, and it will keep growing and growing and growing. Okay, if it is very close, if it is a very slow moving source, the train is slowly moving, you will hear pretty much the same same as the emitted. The frequency you hear will be very close, right? But if it is very close, the frequency will shoot up. Okay, so V divided by V minus Vs will rise rapidly. That's why in some cases you're really bothered by the sound of something which is approaching. Okay, so V minus Vs in the denominator, right? But when it is moving away from you, it is V plus Vs in the denominator. Okay, so when it is moving away from you, it is V by V plus Vs. Therefore, the sound appears to, the frequency of the sound starts to diminish. The frequency of the sound starts to diminish. So when it is moving away from the station, the frequency starts to go lower and lower. Okay, until and of course, there and it is related to this particular equation. Now, what about the case when both are moving, right? When the that is the you are running, you are in a listening to someone, and you are sitting in the train, and there is a beautiful musician playing outside, right? So then what happens is the V motion will move here to the numerator, V observer, right? Observer is moving, you end up with something in the V observer getting added in the numerator. Okay, if the source is moving, right, you end up with the V source getting added in the denominator, with approaching being negative and departing being positive. So when it departs, it slows down. When it approaches, it grows. Okay, so it goes in the denominator if it is the source, right? The observer moving goes in the numerator, right? And again, when the observer is moving towards the source, right? The observer moving towards the source, that is, you're moving towards the station. There is the flute is in the station, right? Then again, your frequency will go up, right? Whether he is coming toward, when the source is coming towards you, or you are moving towards the source, it's the same thing. It will go up. Only thing is, in one case, it will go up because of the source is in the denominator and it is subtracted. The other case, it will go up because you're adding it to the velocity in the numerator. Okay, so V plus V naught by V is going to lead to an increase, right? And similarly, V by V minus Vs is also going to lead to a increase. So if the two sides are moving closer, it is going to lead to an increase. If both are moving, you will end up with V minus VO divided by V minus Vs, or vice versa, based on this person is moving towards, that person is moving away, etc., etc. Okay, so that is the key thing there. So look to solve all these problems. Remember these 4 rules. Okay, and so that is the change in the frequency because of relative movement between the two sources discovered by Mr. Doppler. Okay, so what is the effective distance that the observer sees between the two maxima? So that is the key thing. The effective distance between the two maxima is changed because of the relative motion. Okay, and therefore see a corresponding change. Okay, so when the motion quickens when you're moving towards each other, and it declines when you're moving away from each other. Okay, so that is the basic idea there, and that's what he's saying. The observer hears the second maximum at t2 prime versus because of it takes time for the wave to reach the person. Okay, so there is a time for the wave itself to be to reach, and that is changes based on the two people. So v plus minus v naught divided by v plus minus vs. Remember this one formula, and remember that towards is negative vs, observer towards is negative vs, observer source towards is negative vs, observer towards is plus v naught. Okay, so plus v naught is observer moving towards the source, source moving towards the observer is negative vs in the denominator. Okay, so one is minus, the other is plus for the towards. Okay, so source going towards the stationary wall and receiving its sound back. Okay, so now let v be the sound of the emitted frequency by the source, and v prime be the frequency received from the wall. The final frequency received back by the source in this case will be given by this. Okay, so now you have both motions. So you have the reflected wave, and person moving towards, he has both a ongoing wave and a reflected wave. Therefore, what he will hear is that value. Okay, and therefore v prime is given by v plus vs by v minus vs times mu. Okay, so here's a Doppler problem. A train is moving on a straight track with speed 20 meters per second. Okay, it is blowing a whistle. The percentage change the frequency heard by a person standing near the track. So the observer is stationary. V naught, VO 0, VS 20, right? It is blowing its whistle, is moving on a straight track with, okay, the person, okay, as the train passes him, right? The percentage change in the frequency heard, right? So now when it was coming towards him, right, it is V by V minus Vs times V emitted. V emitted is 1000, right? V by V minus Vs, 320 minus 20, right? So that is 320 by 320 minus 20 will give you the received. When it is leaving, it is 320 by 320 plus 20. Therefore, that the difference between 320 by 300 and 300 by 340, that will give you the percentage. That is about roughly 40 by 340. Okay, so what is the difference? What is the change? It is roughly 40 by 340. Okay, so it is roughly 12%. Otherwise, you can do the calculation and get exact values. You still get the same answer. A1 minus A2 by A. Okay, by A1. Okay, so that will be the change, right? So so you note the final, note the initial, and then look at the change. Okay. So that is as far as this week's class goes. What I am going to suggest is that you spend some time. Let me go back to the beginning of our slide presentation. I hope you can see this slide, right? So What should students do? Students, if you are a NEET student, you download the NEET app. If you are a JEE student, download the JEE app, okay, which is Ramanujan. Okay? Go to Play Store and look for com.jnanamarga.ramanujan, NEET student com.jnanamarga.sushruta. So you listen to, maybe there'll be two lectures from IIT PAL, listen to the two lectures, read the NCRT textbook, and then you attempt some problems. Okay, that is the way to proceed. Okay, you you will find it initially a little bit difficult. Note the formulas that we have taught over the two classes, right? And then read the formulas, look at the slides, right? Note down the formulas, read the solve problems in the NCERT textbook, read the chapter, and then go from there. Okay, solve problems. You will get a lot of problems relating to this. Do one after the other, tuck, 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 tuck. Then you would have revised one chapter. That's how you must proceed. Okay, chapter by chapter, one by one, you must go. Okay, and you must build confidence and have a notebook. Okay, in your notebook, you write the material you're learning. So when you flip back, you will remember. If you write also in the notebook, you will remember what you have learned. Okay, so you keep the phone, keep the notebook also a little bit bigger. Of course, I suggest that you strongly suggest that you go for a tablet solution. Otherwise, you get a tablet yourself and go for the solution, right? So the other point I want to make is, this is HC Verma. It comes with our tablet. Okay, if you are not buying a tablet, I suggest you think of buying HC Verma, which is not expensive. Okay, and in HC Verma, the waves on a string is 15 in book one, and it is 16 in book two. They also have solved problems, and you can also work on those. Look at the solved problems, and then look at the unsolved problems and solve those also. Okay, when you do the due diligence, you spend the time, you invest the time, you will get the marks. Okay, physics, there is no two ways about it, sir. Okay, so with that, I am going to end today's class. Remember to invest time. Okay, invest effort, and then you will be in very good shape when the exam comes. You will be, of course, finding it that you have less time to spend with friends. But if you are studying, eventually you will find that in the exam hall you have more time to do more of the problems and get a better result. Okay, no easy answers, sir. That's why I make it a point to explain to my students so that they are ready for the exam. All right, so with that, I'm going to end today's lecture, and we are going to be returning next week, and I will move on to the next set of material, mechanical properties of matter, etc. And then we will go on to additional material, including and we'll try to catch up on the electromagnetic waves, and then we'll go to material relating to light, etc. Okay, and we will then also move on to thermodynamics and move forward. Okay, so that is how we proceed. Our aim is to keep the two tracks 11 and 12 going in parallel. Okay, with that, I'm going to end today's class. Thank you very much.